Hi, grade 11s. Welcome to my YouTube channel. Today we're going to look at the topic called atomic combination, and in the atomic combination specifically, we're going to look at the polarity of molecules. Guys, the topic before this, it's the polarity of bonds. Check my previous video on this. Now I'm going to look at the polarity of molecule. Now let's look at for example, I want you to define to you what is polarity. What are we talking about when we talk about polarity and the dipole? Um, let's look at this neutral sphere here. This neutral sphere here, it has an equal positive and negative charges here. So we know something that is neutral, the protons and electrons are equal, right? And then now we're bringing sorry, this negatively charged ruler towards it. So this negative charged ruler, what's going to happen? The electrons will be attracted to the positives there, which is the protons. So the protons will sit in this side of the sphere, and then the electrons will be repelled away from the ruler there. So what do we say here? We say this, it has two poles. Do you see? It has a negative pole and the positive pole in it. So this one is a dipole. So the word di means two. It has two pole. It has a negative pole and a positive pole. It has a dipole, so it has two poles. So in other words, this sphere is polarized. It's polarized, right? And in other words, it's what? It's polar. So something that is polar, guys, it has an uneven. Something that is polar. So now this is polar. It means that it has an it has an uneven distribution of charges, right? Something that is polar. Now something that is non-polar, we must know that it has an even distribution of what? Of charge. Right? Now let's go to molecules. Now let's take molecules. Let's take hydrogen gas. Hydrogen gas is a diatomic molecule. So how the bond is formed there, it's a valence electron of one hydrogen atom and one valence electron of hydrogen atom they share. So these two electrons, we call them bonding pair. Bonding pair bonding pair of electrons. So now what is happening here? The electronegativity of hydrogen is 2.1 and the other hydrogen is 2.1. So that means the way they attracted the shared pair of electrons is equally, right? Is equally, right? So they attracted the shared pair electrons equally. So these arrows that are just shown here, we call them dipole moments. Those arrows there, dipole, we call them dipole moments, right? Each of them. So those arrows are equal, right? So if you can represent them in terms of a vector, you have an arrow that is going in this side and you have an arrow that is going in this side. So looking at those that as a vector, technically we said the net vector there is what? Is 0. So but now we don't talk about the vector here, we say the net dipole moment is 0. So once the net dipole moment is 0, that means the hydrogen molecule is what? Is nonpolar, right? And therefore there's a what? There's an even distribution uneven distribution of what? Of charges. So guys, no net dipole moment here. The net of these two, do you see, if you can look at, say it's negative 2.1 and positive 2.1, so the net dipole moment of those is what? Is 0. If you look there, there's like no resultant there, which means there's no net dipole moment, which is the net dipole moment is 0. If there's no net dipole moment, that means the molecule is what? Is polar. So this molecule is polarized, right? Now let's look at this molecule, which is HBr. HBr, it's like that. They bonding. I'm not gonna show the lone pairs there. So in the periodic table, the Br has a greater electronegativity than the hydrogen in the periodic table, right? So the resultant here, so if Br pulls more the electrons than the hydrogen, so we'll say the Br is slightly negative, and then the hydrogen is slightly positive. So that means the negatives will flock in this side because Br is pulling the pair of electrons towards itself. So the negatives will be in that side, and in the hydrogens there will be positive that are flocking in this side. If you look at this, it will be something like this. This is the hydrogen, and the Br will be there like that. So there will be negatives here, and this side there will be positives. Do you see this? It has two poles, right? If you see this one, it has two poles. It has a negative pole and a positive pole. So this one is what? Is dipole, right? It's dipole. And if you look in terms of the dipole moments, if you draw the dipole moment of HBr and the dipole moment of what? Of hydrogen there, do you see you can draw the resultant? There is a resultant there. There is a net dipole moment. So the net dipole moment here is not equal to 0. Therefore, the HBr molecule is a polar molecule. And there is an uneven distribution of charge. The uneven distribution of charge, it happens when there's one that pulls more than the other. So Br pulls more the shared pair of electrons towards itself than the hydrogen due to their electronegativity. So HBr is a polar molecule and is a dipole. Let's look at this molecule now. Let's take water, H2O. The shape of H2O, guys, it's like this. It's a band shape. It's an angular shape. It has two lone pairs there, right? And now we're going to look at each bond. This bond is equivalent to this bond, so we're going to look at this bond, and then it means the same with this bond, right? So we're going to look at these two. So which one between the hydrogen and oxygen that has a greatest electronegativity is high? It's oxygen. So that means that the oxygen will be slightly negative and the hydrogen will be slightly positive, which means the electrons will migrate from that side to that side. So the dipole moment here will be in this side. So I won't draw for both, I will just draw the resultant there. So guys, what you can do here, these arrows these two arrows they will form a resultant that goes this way, right? So here there is a dipole moment, or alternatively what you can do, I will draw the vector diagram starting with this one and do this one. So here, this one, this dipole moment, and then I'll draw consecutive dipole moment of this. Don't worry about this, this is a resultant. So the dipole moment of that is gonna go this way, which is this one is this, and this one is this. And then the resultant, I started with this one and then I ended with this one. So when I draw the resultant, I draw it from the tail of the first vector to the head of the last vector. The first vector was this one and the last vector was this one. So the tail of the first vector to the head of the last vector. So looking at this, guys, this is a what? Is a net dipole moment, right? So the net dipole moment is not equal to 0, therefore the water is what? Is a polar molecule, right? Okay, we can draw this alternatively because we started with this and then we ended with this, but now let's start with this and end with this and see if it's gonna yield the same thing. So here's it, and then I'm gonna draw the other one, which is this one. Here's it, our resultant. You see it's going up again, so it's gonna go up. So here is a dipole moment there. So hence here there is an uneven distribution of what? Charge, right? Let's look at another molecule that is polar. Okay, I shouldn't spoil it and tell you it is polar. NH3. NH3, its structure, it's like this. So we'll get to know when we talk about the shapes of the molecule why it's like that. It's a trigonal pyramidal, but it doesn't matter. So now when we look at the bond, this bond is equivalent to this bond is equivalent to this bond. So the one that is highly electronegative between the hydrogen and nitrogen is nitrogen. So the electron will migrate to nitrogen, and the electron will migrate to nitrogen, the electron will migrate to nitrogen. So the nitrogen will be slightly negative and the hydrogen will be slightly positive, slightly positive, slightly positive. Eventually, that means the positives are here and the negatives will be here. Do you see there will be two poles? There's a negative pole and the positive pole there. So that means this is what? This is what? A dipole. Something that is a dipole, that means it's something that is what? Polar. But now let's prove that in terms of the vector diagram. So I'm going to draw a vector diagram, but I'm going to start with this. I'm going to go this way. I'm going to go this way, or I can draw them this way. So I'm going to start with this one. Here's the first vector, and the second vector will be this, straight up, and the last vector, it's like that, right? And then when I draw a resultant, I start from the tail of the first vector to the head of the last vector, right? So do you see there is a what? there is a net dipole moment. The net dipole moment is not equal to zero. Therefore, the ammonia is what is a polar is a polar molecule, right? And also there is an uneven distribution of charge. Now let's take another one. Let's take another one that I think it's polar. Okay, let me not share it. Let's take the CH4, which is the methane gas. So the methane gas, it's a carbon in a central, and then there are terminal hydrogens. There, like that. So the carbon, between carbon and hydrogen, if you look at these four bonds, are exactly the same. So the hydrogens there, they have a less electronegative than carbon, so the electrons will migrate to carbon there. So the dipole moment will point towards carbon. Dipole moments will point towards carbon. Dipole moments will point towards carbon. So if you draw a vector diagram of this, so basically the carbon here will be slightly negative, and then the hydrogens will be slightly positive, slightly positive, slightly positive, right? So when I draw the vector diagram of this, I'll start with this one and go with this one to this one to this one. Or I can start with any. I can start with this and this, is as long as I'm moving in order, this way or this way or this way, doesn't matter. As long as I'm moving in order, I'm not doing a random from here to here to here to here. No, it's not gonna work. I have to go in order, not randomly. So I'm gonna start with this one. You'll see which one that I used, and then I'll do this one. Which means I started with this one, and then this one, and then this one, and then that one, right? And then I'll draw the downward one, and then I'll draw the one going to the left, right? Do you see? This is a closed vector diagram. So this closed vector diagram, it means there's no, the net dipole moment is equal to zero, and therefore the methane gas is a what? Is a non-polar molecule, right? And we know the non-polar molecule is a what? Even distribution of what? Of charge. Alright, I think that makes sense, guys, with the polarity of molecules, if a molecule is polar or a non-polar. Let's look at phosphine, if it's polar or a non-polar. Now phosphine is shaped like this. It's a P with the 3 hydrogen there. That it's caused by the lone pairs. That's why the shape is like that. It's similar to ammonia, but I'm not going to dwell on the shape. Now, the electronegativity of force for us is equal to the electronegativity of what? Of hydrogen. It's 2.1. So now in this case, the dipole moment can go this way towards phosphorus, all of them towards phosphorus, or alternatively we can say, um, um, if we draw again the structure, we can say the dipole moments can go towards to hydrogen, but that it will also tell us the same thing because of their electronegativity is the same. So if we can draw the vector diagram of that, I will start with this one and then this one and this one, right? So it's going to be that, and then this one, and then that one, right? So the net dipole moment will be there from the tail of the first vector to the head of the last vector, right? Or alternatively, for this one it will be the same. So we'll start with this one, which is this, and then we'll go to the middle one, and then we'll go to that one, right? And then we draw from the tail of the first vector to the head of the last vector. So from the tail of the first vector to the head of the last vector. So it doesn't matter. So here, if you look, there is a net dipole a moment is not equal to 0 there. Therefore, the phosphine is what? Is polar. That means it's what? It's dipole, right? It means there's an uneven distribution of what? Of charge. Distribution of charge. Let me do the last one, very last one. It's the tetrachloride, carbon tetrachloride, which is CCl4. Right? We have a carbon as a central, and we have chlorines. Tetra means 4, carbon tetrachloride. That means we have carbon bonded with 4 chlorines. So chlorine has a greatest electronegativity than carbon, so the dipole moments will go towards chlorine, 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 like that. So we have that. So I'm going to start with this one, and then this one, and then this one, and then that one, right? So I start with this one, this one, this one, this one. So I'll go, is that anti-clockwise? Clockwise, yeah. So it will be that, right? And then that, and then that. So do you see? No, right? Net dipole moment is equal to 0. Therefore, the carbon tetrachloride is what? Non-polar. Non-polar. It's non-polar. Okay, guys, I hope you understand and it makes sense. Cheers, bye.